So let's take a look at a dipole in an electric field. So if I have a uniform electric field, and just write out uniform, there's formal ways I can write that, and just for the fun of it, because what the heck, it is physics. So what I'm saying is that if I've got sort of an x and y coordinate system here, that dE dx is equal to dE dy, which is equal to 0. I'm just saying that the electric field changes with respect to x. Not at all. There's no change. The electric field does not change with respect to y. That's just a fancy way, without the calculus version, that the change in E over the change in x is equal to the change in E over the change in y, which is equal to 0. Notice I'm not throwing out the idea that it might or might not change with time, but we really don't care about that. We're just taking a look at a snapshot here. I have a positive charge here, some positive Q, and I have my negative Q charge over here. It is a dipole that we're talking about here. There is a distance between them of S. That is the distance between them. Because it is an electric dipole, there's an electric dipole moment that is pointing in the direction from the negative to the positive. And this is the magnitude, let's write that, the magnitude of this electric dipole moment is equal to S times Q, just as a reminder. And again, this P is for electric dipole moment. It is not for momentum, because we have only, basically, if you look at all the capital and lowercase Greek and Roman letters, basically our alphabet and the Greek alphabet, upper and lowercase, we have 100 characters. So we've got far more quantities than that, and so there is unfortunately some repeat. Because this is an electric field, we have some forces involved here. We have a charge in an electric field. I know positive charges are forced in the direction of the electric field. So I have some force on the positive charge here, and the negative charge is forced in the other direction. Opposite. The negative charges are forced upstream, and these are forced downstream. I have some midpoint right here, and this angle right here I'm just going to call theta, because I'm just incredibly clever when it comes to naming those things. If you actually want to show that you are a rebel, pick a different Greek letter. But don't use pi. I don't care how much of a rebel you are. Using pi is just stupid. Using pi for an angle, for a variable. I have run into that once. There was a astrophysics book I was doing a self-study on, and suddenly pi showed up in an equation, and I was trying to think of where does pi come from? And after about a half hour, I suddenly realized that pi was a variable. Ugh, how could they? Anyway, maybe that's just an astrophysics thing. Those people are crazy. Brian May. All right, anyway. So I have forces acting on it, and it's going to cause it to rotate, and so therefore we have torque involved. So let's do a reminder that torque is equal to R cross F, where this is the moment arm and this is the force that's being applied. Moment arm is a vector from the pivot point to where the force is applied. So because there's an equal amount of force, magnitude of force applied to both sides, just opposite directions, this is not Newton's third law in play here. Since there's an equal magnitude of force acting on both objects, it is going to cause it to twist about the center. So another reminder, if I have my R this way and my F that way, if I do R cross F, the direction, let's set up a coordinate system here, I, J, and then a right-handed coordinate system, K is coming out. So I cross J is K. So that's coming out. So when I'm doing a cross product here, I put my hand in the direction of the first vector, which is R. So it's that way. I want it so that my fingers are along that plane there, so somewhere along in that direction. I want it so that when I bend my fingers, they bend towards the second vector. Well, since my second vector's there, I'm going to do a cross product, and that's going to be downwards. And so the direction of the torque in this case would be in the negative K direction. If I had R this way and F that way, then when I do R cross F, I have R going like that, F, my fingers bend that way to go to F, so my thumb points up, And so here, the direction of the torque would be in the positive k direction. If this is all incredibly new to you, you've never done torque with cross products or anything like that, then you probably should see those videos, which are out there. And hopefully I'll remember to throw in a link just for background information. Another thing is that the difference between a cross product and dot product is a cross product cares about perpendicular components. And so I could also find the magnitude here if I figure out how much of r is in the direction of f. So if that angle there is theta, this would be r cosine theta from here to here, and r sine theta from here to here. If I do a dot product, I'm multiplying r cosine theta and f. But for a cross product, I'm multiplying r sine theta times f. Or over here, I can figure out how much of f is in the direction of r. This would be, if that angle there is theta, this would be f cosine theta, and this would be f sine theta. With a cross product, you're multiplying perpendicular parts. So I have f sine theta times r. Either way, r cross f would have the magnitude of r f sine of the angle between them when they are tail to tail. So for our first vector here, or for the first torque, well, let's do it this way. Torque is equal to the torque acting on the positive charge plus the torque acting on the negative charge. So this would be the r positive cross f positive plus the r negative, so the moment arm to the negative charge, cross the force on the negative charge. And my r and f, that right there, that's my r positive. And my r negative, again, the moment arm is from the pivot point to where the force is applied. So that's my r negative right there. Fine point. Why does anyone ever use fine point? Well, because they're desperate. R cross f here. So I have r going up in that direction right there. So there's my r positive. My f is to the right. So the angle between them is indeed theta. R cross f would be in the negative k direction. So this is equal to negative this r positive times the force on the positive charge times the sine of theta in the negative k direction. So it's r f sine theta in the negative k direction. Down here, I have r going in this direction. That's my r negative. My f negative is to the left. And if I do r cross f, so that's r cross f, it's also in the negative direction. So negative r negative f negative sine theta, because the angle here is also theta. So that is the magnitude there in the negative k direction. R is equal to 1/2 of s. That's true for both sides. So I get negative 1/2 s. And then negative 1/2 s. The force is equal to, well, it's a charge in electric field. So that's magnitude of that is Q times the electric field. And I'm going to do electric field strength this way instead of just writing the same old E, because I believe in the next video we'll be dealing with energy times the sine of theta. And over here we'd end up with Q E sine of theta. And they are both in the k hat direction. These are the same thing here. So what you end up with is here, I got that plus that. So the halves are going to go away when I add them, because 1/2 plus 1/2 is 1. And so I have negative SQ, magnitude of my electric field, sine theta k hat. Now think about this. We can simplify this just a little bit here. I know SQ is the magnitude of my dipole moment, my electric dipole moment. And so I just have, this is my magnitude of my electric dipole moment times the magnitude of my electric field times the sine of theta. That's just a cross product. So the question is it P cross E or E cross P? Well, I know it's going to be in the negative direction. So if my electric field is to the right, and P is that way, which cross product is going to give me one in the negative k direction? Well, negative k direction is down, so it'd have to be P cross E. And so this becomes P cross E. And that is the formula for torque acting on a dipole in an electric field. Now, why is this necessary? Well, part of it is just an exploration of the physics of it, and part of it is the exploration of the math, just to remind you of some things. But one of the critical things here is that when we bring in dielectrics, if I take a insulating material and put them between two electric plates which are charged, that the molecules inside that are going to start to rotate. And as they rotate, notice that as this thing starts to rotate around, it will oscillate back and forth, but has a tendency sort of to be in a particular orientation, that this has an electric field going from positive to negative. We have this electric field, the smaller electric field, so I'm going to call it E2. So I have two electric fields here. I've got this external electric field, and then I have this other electric field coming back the other way. And so what's going to happen is the net result is that in this localized area here, I have a smaller total electric field. And that becomes critical when we start dealing with capacitors.